we have an antenna with impedance ZL equal to 70 plus J150, which is connected with a transmission line of J100 ohms. As you see, the transmission line impedance is different from the antenna impedance. Therefore, there will be a reflection because of the mismatch of the impedance. Now, we have to design a system that has no reflection, no standing wave. And we can do that by using a open circuit series stub to make the system reflection free. So in this case, you have to find the impedance of the stub, the length of the stub, and the distance of the stub from the load. So let me sketch the configuration here. Let's say you have a transmission line. We choose a two-wire transmission line, and this transmission line, one side is connected with the load. So this is my antenna connected over here. The impedance of this is 70 plus J 150, and we connect source or generator at this side. The impedance of this is Z0. This line is Z0 equal to 100. So we'll find the reflection in the system, and to make this system reflection free, we have to add a series open circuit stub. The idea is, let's say you have ZL normalized. Just ZL normalized, I use lowercase zl is equal to uppercase ZL over the Z0 is equal to zero point 0.7 plus J 1.5. So basically, we have to make this entire system is equal to 1. So we have to make this will be my final impedance, that must be 1 to get reflection free system. So if you look at this Smith chart here, so the load is located at this point, that is zero point 0.7 plus J 1.5. If you can move somehow at this point, then the system will be reflection free. We need to go to the center because the radial distance from center to the load indicates how much reflection or how much power will be reflected back. What will be the coefficient of the reflection or reflection coefficient? So the radial distance from center to the load indicates how much power will be reflected back, or what is the reflection coefficient. So now, how we can do that? So just as I want to get 1 here, so let me find this value, fix this value to 1 first. So let me find something equal to 1 here. So from here I want to make 1, and that time we don't care about this value. I think we are not interested at this point. At this point I want to make the real part equal to 1. So this first thing I want to do. So how we can make the real part 1? So go to the Smith chart now, and if you look at this Smith chart, you can see the center. So you can see the center here is the R equal to 1 line is somewhere here. So at this point you have R equal to 1. R equal to 1. So we need to move from the load up to this point. We have to move from the load up to this point. So at this point you have R equal to 1. R equal to 1. So just I am going to go R equal to 1 up to this point. Now let me draw a line. So let me draw a line here and see the distance between from this I find the distance from here to here. To here. So this is the distance ds. So distance is this much. So what is the distance here? Let me find the value of, you can find the value of lambda. Here is 16, 162, 164, 165, 166, 167, maybe 0.167 lambda. And from here you can find 182, 184, 0.185 lambda. So to find the distance between these 2 points, so I got distance of the stub from the load. So that is the ds. So ds will be 0.185 minus 0.167 lambda, 0.18 lambda. So this is the distance of the stub from the load. So you might see there is another point right down here, right down here. So this will be another location for a stub. But this is the closest one. So this is the closest to the load, right? So this is the closest one. But this is the nearest to the load. And this is called nearest to the generator. So if we ask you to find the stub nearest to the load, so you have to find this. If we ask find the stub distance nearest to the generator, you have to find this one. So I am solving nearest to the load. If we don't mention anything, you can find nearest to the load. So this is the nearest to the load. So now we found this stub location. So we found the stub location. Let me put my stub here. So just this is something. So we put my stub here. And the distance from the load to this stub is ds. So we already find this. Value. Now at this ds, what will be my value now? So we got this value now. So this is 1. This is very for sure. This is 1. And what will be the value here? This value must be positive x. But if you choose somewhere here, this value will be negative x. But this point has positive x. So let me find the x values now from the Smith chart. So if you choose to this value, so this intersects point goes to this point. So this value here, so this is 1.8. So this value is 1.8. So you can write 1.8. So I write the x value here is 1.8. So now we got the impedance at this point. So if you look at the impedance here at this point, so initially our impedance was 70 or 50, or the normalized value was 0.7 and J 1.5. So the normalized value was 0.7 and J 1.5. Now I moved toward the generator. So this is toward the generator here. So this is toward the generator. So I moved toward the generator and got a new impedance. So the new impedance here, the Z prime, is 1 plus J 1.8. So this entire part now behaves like a load, creating this entire part as a load. So this is like my new load, and that got an impedance like this. So and we got R equal to 1, but we have to remove this imaginary part. So how we can remove this imaginary part? To remove this, we have to add an opposite type of reactance, like capacitive reactance of 1.8. We have to add a stub here. So this is my stub here. So we have to add a stub here, open circuit stub. So this is my open circuit stub, and this stub, the stub x must be negative J of 1.8, because then if you add negative 1.8, j negative 1.8, then the system will have only one, right? It will be reflection free. Therefore, we need z stub is equal to 0. So this is my lower case, and this value is negative j 1.8. But if we want to find uppercase z stub, then we have to multiply with z naught, and this value will be 0 minus j 180 ohms. So this will be my stub impedance. So that's the answer for part A. So we solve for part C and part A. Now we have to find the stub length. So how we can find the stub length? To find the stub length, basically we see we have a stub like this. So we have a stub like this. So this is my open circuit. So this is open circuit stub. So this impedance will be ZOC. And ZOC is basically infinity. The open circuit impedance is infinity. And you have to find the impedance at this point. From looking from here, must be at this point will be negative j 1.8. So the length should be chosen like this. So the length will be like this, so that you can go from infinity to negative 1.8. So now let me find the infinity point from the Smith chart, and then find negative 1.8 from the Smith chart and their distance. So impedance infinity will be here. This is my infinity point. So this is my ZOC, or infinity point, and look at 1.8. 1.8 is somewhere here. 1.8. So now this is my infinity point, and we are moving from infinity toward the generator. So this is toward generator. So now we are moving from here toward the generator. That means in clockwise direction up to this point. So this point has 0.25 lambda, and this is 0.33 lambda. 33 lambda. So now the distance here to here is the stub length, because if you choose go from this mass to this mass, that will be a stub length. So length of a stub will be 0.33 minus 0.25 lambda. So that will be 0.08 lambda. So if I write down here the answer for part B, then it will be length of a stub LS is equal to 0.08 lambda. If lambda is given, then you can find something in meter. Just multiply with the lambda, you will get the length in meter. So why this is a stub length? This distance indicates a stub length, because the expression of impedance, but like that is equal to Z naught ZL plus Z naught tan beta L over Z naught plus ZL tan beta L. Now if you put Z over Z naught is equal to, here you can write 1 plus Z naught over ZL tan beta L, and here Z naught plus Z times ZL plus J tan beta L. Now Z naught as ZL at this point for the stub, this will be for a stub, this is the load, right? Per step, this is the load, and this is my the characteristic impedance. So this is the stub characteristic impedance, and this is the load of the stub. So the load is open circuit here, and this is the characteristic impedance. So if you say the character ZL is open circuit, so that's infinity. So this gives back to 0, and this goes to 0. So you'll get normalized Z equal to negative Z cotangent beta L. So you see here the impedance now, the impedance is like the impedance is like cotangent of beta L. So that has a imaginary part, negative imaginary part, and the value is defined from cotangent beta L. So this is the length basically. Beta L is the length. This is called the elliptical length. If you substitute beta or divide this value by beta, you will get the length. So whatever you got, cotangent of beta L is equal to Z. So the value of Z, value of the stub impedance. So stub impedance depends on the stub length. So here the L or beta L you can find from here. So this is basically cotangent of beta L, cotangent of beta L, or you can find this is like the equivalent to the length. This is equivalent to the length. And equivalent to the length is equal to the impedance. So we are finding the equivalent length to obtain this impedance. So just our step impedance is negative 1.8, and to obtain negative 1.8, how much, what will be the length of the step? So you starting from here and find that much length. So this is how we can find the single open circuit series step to make the system reflection free. So here we are adding a series step, open circuit series step to make the system reflection free. We are going to solve the very same problem. In this case, we have a short circuit series step. So let me draw the transmission. Let me draw the transmission line here. And in this case, we are going to use a series step, short circuit series step. So here we have the load. Basically, the second wire is nothing but a short circuit, but a ground wire or something like this. It could be ground wire or returning path of current. So we don't care about the second wire, just we are caring about this. So this is the load ZL. So let me write the normalized value, that is zero point 0.7 plus J of 1.5, and we have to find the distance here d. This is the very same distance that we obtained before, and we have to find the length. So distance d, so impedance at this point, so the impedance, let's say Z prime, will be 1 plus or minus Jx at distance d, distance d. So now we have to find this value Z prime. I write lowercase. So Z prime equal to how much? 1, and what will be the value of this? So let me go to the Smith chart. So this point is here. So on this point, I can draw a straight line. So if you draw this straight line, you can find the distance between these 2 points. The distance from this point to this point, 0.167 lambda. So we find this point is 0.185 lambda. So now the value for x. So if you go here and again expand this and find the value for x, so x will be 1.8. So So if you see here, this value is 1.8. So you can write 1 plus j of 1.8 at distance is 0.185 minus 0.167 lambda. So that means d equal to 0.810 lambda. So 0.018 lambda is the distance from the load to the stub. Now you have to find the stub impedance. So this is part C. So now you have to find a stub impedance. So stub impedance will be Z stub. I used lowercase, so it will be 0 minus j of 18. Because this is plus, so to cancel this you need a negative. So we found this one. So if you want to find the uppercase stub impedance, then you multiply this with 100, that will be 180 ohms. Now you have to find the length of the stub. So length of the stub is, you see the stub is here, so you have to measure the length from this point and move this direction toward the generator. So move toward the generator from this point. So this is the short circuit point. So this is ZSC, short circuit, and ZSC equal to 0. And on the Smith chart, this value is ZSC. So this is ZSC, that is equal to 0. So you have to start from here and to go all the way to negative 1.8. So if I see the Smith chart here, negative 1.8 is somewhere here. So that is, if you see the location, this will be 0.033. Sorry. So 1.8 is somewhere here, and this is 0.33 lambda. So now we measure the distance. So measure the distance from here and we move toward the generator. That means clockwise direction. Don't go this short way because we cannot go anti-clockwise. We have to go clockwise direction. So you move this way, this way, this way until you reach there. So this is the distance from this point up to this point. So this is the length of the stub length, and then stub length B. Stub length will be LS, will be, this point is 0 and this is 33, so you can write 0.33 lambda. If lambda is known, then you can multiply the length and the distance with lambda and find the value in meter.